Hello everyone. So today we're going to start on 7.4, but actually before we start on 7.4, we're going to actually talk a little bit about 7.3. So there is no homework assignment for 7.3. There are only three theorems that I want to introduce in 7.3, and then we're going to get started on 7.4. So these theorems are very straightforward. A majority of these come directly from BC calculus. Also, they are actually counterpart of these theorems in BC calculus. So that's the reason why we just go quickly go over them. It should be pretty obvious that where they are true or not. So we're actually going to talk about 7.3, which is basically called integration theorems. Okay, and there are quite a lot of them in 7.3, but we only go touch up on these three. So the first one is theorems 7.3.1, which basically refer to as the linearity of Riemann integral. So what does that mean is this. Let's say we're given two functions. Let's say function f and function g. We don't really care about what the input is. We're assuming that input would be a vector in Rn. And let's say we're given this function f and g, and let's say that they are both integratable. Simply just mean that they have an integral over a region B. So therefore, what does that mean is this? It means that both integral over b f of vector x dv and integral over b g of vector x dv, they both exist. That's what the word integratable mean. Meaning that when you integrate, you have an answer. Let's say we have two scalar. Let a and b be two constants. Then what we know is the following. Then we know that if you take an integral over b of a f of vector x plus b g of vector x dv, I can actually separate this into two separate integral and pull out the constant from the integration. And therefore that would actually equal to a integral over b f of vector x dv plus b integral over b g of vector x dv. So that property is often referred to as a linear property. Okay, any function or any operation that has this property is referred to as a linear operation. And sometimes students often don't understand why is this operation important, because once again, I mentioned this before when we did chapter 1. Okay, a lot of these properties that we know in math, they're important because they allow us to override an order of operation. In here, the operation is that on one hand, on the left side, you have to combine the function f and function g with the coefficient a and b, then you integrate. While on the right side, it said that you can actually integrate f and g first and then do the same exact way to combine them together, like you would when they were inside the integral. So therefore, you can actually override the operation to either combine first, then integrate, or integrate, then combine. And this property allows us to say that no matter which way you do it, you get the same result. And that offers a lot of flexibility when we're dealing with evaluating expression. Because sometimes we just can't combine them, and then we're stuck. But this tells us that no, it's okay. If you can't combine them, just don't combine them. You just integrate first. Then you combine them. It's perfectly okay. So these theorems are extremely important. And the linear property is actually a very powerful property that we will talk about more for those of you who are going to be my student next year in differential equation. But even not that, you also learn a lot about linear in this year, chapter 1 and chapter 2. The next theorem is not as important, but it is something that's good to know. It's theorem 7.3.2, which states the following. okay, if you are given a function f of vector x, and we know that this function is always greater than 0 over a regions B, then what we know is that if you integrate it over the regions B, you always get an answer greater than or equal to 0. Students often get confused because they somehow feel like whether the integral is greater or less than 0 is somehow tied to the regions of integration. Actually, it does not. It's actually all depend on what happened to f. So even if you have a region that involves positive and negative values, is perfectly okay. If your function f is always greater than 0, then therefore imply that when you are trying to calculate the volume under the surface, you are having a positive height, and therefore result in a positive volume. That's how that works. Because the base always going to give you a positive area because of the way we define it. So important to know that if the function is greater than 0, then what you're looking for is always greater than 0 when you integrate. And that's why when you have a function that's always greater than 0, whenever you integrate it over regions, you get what we call volume. Not net sign volume, but just strict volume. Okay? The last theorem is theorem 7.3.6, which we actually kind of use that theorems already in 7.1 when we talk about it, actually on the last video 7.1, but we now formally define this. So which is this? Let's say if f is integratable over two disjoint regions. So the word disjoint meaning that they don't overlap. Let's say we call it B1 and B2. Then we can say that if I want to integrate the union between B1 and B2, f of vector x dv, I can simply integrate over B1 and then integrate over B2 and then add the result together. Which, if you think about it, make perfect sense from a geometrical standpoint. If you have a regions B that's split into two, if you want to find the volume over these regions, well, that would just basically mean that you basically splitting the solid that you try to find the volume into two pieces. But when you combine them, you still get the same exact volume. Okay, so that's pretty obvious. And as a matter of fact, we kind of use this right here. That concept is given right here, where if I want to find the integral of these entire regions, I can separate into two separate ones and just do the two separate integral. Okay? So that should be relatively obvious. Oh, I actually did not realize I did have a 7.3 integral theorem. So I guess this is now going to go be in 7.4. All right. Yeah, I'll probably fix it later. I'm just put this in 7.3 so that way it's organized properly. All right. So, all right. Now I just paused the video and fix it. So now it's in 7.3 now. So now that works. So that will be a theorem that you actually learned that in BC calculus also, where if you have an integral from A to B and then integral from B to C, then you can actually combine them together to form the same exact value as integral from A to C. This is the same exact concept, except that we're using two-dimensional regions or higher dimension regions. So that's actually conclude the three theorems that I want to show you. So first one is that it's extremely important that you can actually move constant through a Riemann integral, and you also can combine or separate Riemann integral when you have a sum or difference. And when you have a function that only gives positive value, you're actually finding the volume, not the net sign volume, which is what this theorem tell you. And then finally, the last theorem right here, it basically tells you that you can actually subdivide a region into disjoint regions and then integrate them and combine the result. The key is that they have to be disjoint, because if they overlap, then you will basically double count some of the area of the volume. That's not good. All right, so now what I'm going to talk about would be 7.4. So 7.4 talk about something called change of variable. So what does it mean by change of variable? So actually, change of variable is something that you have already learned. And I actually mentioned that to you before. When we talk about change of variable, basically just mean that when you have an integration in one variable, you change it to a different variable. And if you think about it, wait a minute, that explains something that you hopefully remember. And that's called U substitution. Oops. So U substitution is basically an example of change of variable, because you're basically changing the variable from X to U. So last year in BC Calculus, you learned a technique called U substitution. So we're going to kind of go over this, and we're going to use that as a way to learn what are we doing with change of variable. So we've learned a technique called U substitution for integrations. So the way that U substitution worked in last year, which is very different than this year, but let's talk about it, because that way you understand why we need to use that. So last year, when you learn about U substitution, you are basically using it to do one thing. U substitution basically allows us to integrate a composition of functions. So that's the primarily reason why we use U substitution. It's because we have a composition. Okay. However, the different thing about it is that while the concept of U substitution is to somehow allow us to integrate a composition by simplifying our integrand. Well, that is the concept of what U substitution does. It's simplifying the integrand into something that's easy to do. What we're going to be doing with the change of variable is actually not going to do that. It's actually doing something a little bit more different. So I'll show you what that is. But before we do that, how about let's do a simple example first, just to illustrate the technique. Because even though we are using change of variable for a very different reason than U substitution, the technique that we're going to be using are almost identical, except that we're just doing with more variables. So show you. Okay. Oops. All right, there you go. So show you. So let's try a very simple example to illustrate. How about I ask you to evaluate this? So very typical substitution integration problem. Okay? Integral from 1 to 2 x square root of x minus 1 dx. So hopefully you remember what Mr. Ambrose and Mrs. Dillon taught you on how to do this integral. We're going to start the process, and maybe they might do something slightly different than what I'm showing you right now. But hopefully when I start doing it, it makes sense to you and you remember. So first thing I probably want to do is to define what u is. So in this case, I'm going to define u to be x minus 1. And automatically that tells me that x is actually equal to u plus 1. I can take the derivative of u and therefore become du over dx, which actually is just equal to 1. So therefore I can say that du is just equal to dx. And I also do the following, which is a good habit that you should get yourself into, is to go and change the limits. See, the limit is x equal to 1 and x equal to 2. Both 1 and 2 are referred to x value. But since I'm changing it to u, I'm going to go ahead and fix it. So u would actually equal to 2 minus 1, which is 1. And for x equal to 1, u would equal 1 minus 1, which is 0. So now I have everything that I need to change my integral. So this is how it works. So here's my integral. And what I'm going to do is change the following. The 2 will now change into 1. The 1 will change into 0. The x would change into u plus 1, while the radical x minus 1 become radical u. And then dx become du. So that's basically what we normally do in a change of variable or u substitution. Is by changing everything to the new variable. And so after I do that, my integral now actually turns into this. It becomes 0 to 1, u plus 1 times radical u du. And now to evaluate this integral, I'm going to go and say that this is actually u plus 1 times u to the 1/2 power, which then turn into just u to the 3/2 plus u to the 1/2. So that's basically what actually maybe I'll just write a second line. All right, there you go. So that just basically equal to integral from 0 to 1, u to the 3/2 plus u to the 1/2 du. And so that integrates to 2/5 u to the 5/2 plus 2/3 u to the 3/2. Evaluate from 0 to 1. So plug in 0 is 0. Plug in 1, I get 2/5 plus 2/3. So therefore that would be 6 plus 10 is 16/15. That's my answer. Pretty good. So hopefully you remember how to do this. So this is usually referred to as a double substitution problem, because you don't only have to substitute u minus 1, x minus 1 to be u, but you also have to substitute x to turn into u plus 1. So that's usually relatively typical AP exam question. They do like to ask a question similar to this. So hopefully that brings back some memory on what you have done and you remember how to do this. So now think about what happened in this case. So in this scenario, when I do this integration, notice what I did. We did the following thing. So to use u substitution, we basically have to change the following 3 things. From the integral. So what are the 3 things? Number 1, we have to change the integrand so that the integrand now become the new variable. Number 2, we have to change the differential. Okay, and I put an s in the end because for our iterated integral, there will be multiple of them. And finally, we also have to change the limits. So those are the 3 things that we have to change. Okay, and the question then we will try to figure out would be, when we try to do a Riemann integral and try to turn it into an iterated integral, and then when I have an iterated integral and I now try to change the variable, how am I going to change these 3 things? Okay, as a matter of fact, the last thing I'm going to do is I'm also going to say that this basically also referred to as changing the regions of integration. All right, so now before we talk about this, let's talk a little bit about why we're doing this. So what is the main reason of doing a change of variable in a multivariable integral? In a Riemann integral, In the Riemann integral, apply the change of variable So I will not call it a U substitution because the U substitution only defines one single variable. So what we're going to try to do is try to change all the variables. So therefore, a more appropriate term would be called a change of variable technique. To apply a change of variable technique mean the following. Applying a change of variable means replacing all the independent variable to a new set of new set of independent variables. And therefore imply that what we have done, which has the same effect as using a new coordinate system. Meaning, instead of using x and y, we probably apply change of variable to turn them into r and theta, and now we can interpret r and theta in a completely different way than x and y, and therefore allow us to now use a completely different coordinate system to do that. Now, one of the main reasons why we want to do this, okay, unlike last year in change and U substitution, the primary reason of using U substitution is so that we can simplify and complicate the integrand, which mostly involve multiplication between multiple things as well as a composition, into something extremely simple to do. As a matter of fact, if you are doing U substitution last year, you find out that after you make the substitution, the integral that you have to do should be very easy to do. And if that's not the case, you're probably not doing your U substitution correctly. For us, the major problem is not the integrand. We would eventually find some way to work past the integrand. But what's more difficult to deal with is actually our regions of integration. So the main advantage of using a new coordinate system is that it will allow us to turn a complicated regions of integration read non-rectangular into a simpler regions of integration. Read a rectangular regions of integration. So that's the main reason why we want to do a change of variable system. So one of the most common concepts that you probably already think about is, if we want to integrate something circular, that would make sense for us to use a rectangular coordinate system would not work, because a rectangular coordinate system is straight line. But a circular regions would be formed by curve. So therefore becomes something that's, we won't be able to do easily. So one way to deal with that is to learn to change the coordinate system to a more circular friendly coordinate system. And that, of course, is what we call polar coordinate system. So let me show you. So quick recap. A polar coordinate system is basically a coordinate system using r and theta. A polar coordinate system is defined using this transformation. Is basically defined by the coordinate transformation T of r theta is equal to r cosine theta, r sine theta, which is equal to xy. I'm not going to re-talk about how the polar coordinate system work or things like that. The only thing that we're going to talk about is how do I form a transformation. So the idea is actually pretty simple. Is that all you have to do is exactly what we did with the u substitution. Change the integrand, change the differential, and change the limits. So how does this work? So let's define how a polar coordinate transformation would work in a integral. Here's the definition. Unfortunately, it's already 26 minutes, so I'm probably going to state the definition, but we're going to talk more about it in our next video where we're going to do some example on this. So let's say we let B be a region in R2 with, let's say, the XY coordinate system. And let T of r theta equal to r cosine theta, r sine theta equal to xy be the polar coordinate transformation. And let's say we know a regions in the polar coordinates that correspond to the regions in the xy plane. Let D be a region in R2 with the polar coordinate system. So how is this different? The difference is that D is in R theta while B is in xy. Here's the connection. Let D be a region in R2 with polar coordinate system such that if I transform D from polar coordinate system through the polar coordinate transformation, it will actually give me the regions B. Now, it might be kind of like, okay, what does that mean? So this is what it means. If I take a regions in R theta, let's say here's D. If I puck it through T, I get a region in the XY where we call B. It might be a little hard to understand, but I'll show you an example and then you'll see. And if I now have this set up, I have the polar coordinate transformation, I have a corresponding regions B and D in the two respective coordinate system. Now I can make a connection between an integral in the polar coordinate system versus in the xy coordinate system. And this is what it is. Then we can now define a double Riemann integral over B, f of xy, dx dy. Now remember, this is a Riemann integral. So therefore, even though I write dx dy, it doesn't mean we have to integrate dx then dy. Okay, that's not what it meant. Okay, it just means that the two independent variables are x and y. That's all I want to convey. This integral can now be written as a new integral, but no longer in x and y, but instead in the polar coordinate system. And when you do that, this is what happened. It will become a double Riemann integral over D, f of t of r theta r d theta. So important to understand is the following. So remember what we talk about whenever we form an integral, and by applying a change of variable or u substitution, we have to change three things. Number one, we have to change the integrand. The integrand is changed by a composition, which allow us to change the coordinate r, x, and y into r and theta. Two, we change the differential. Now, here is probably the most important part. Okay? The most important part is this right here. See the r right there? That is how it corresponds the two differential together, which is exactly what you do in u substitution when you do this. To try to show a relationship between du and dx, that's what happened here. That's why we have an extra r. Now, you might be thinking, like, where did the r come from? Well, we will talk about that toward the end of 7.4 when we learn something called the Jacobian theorem. So right now, you just have to trust me on this. So note, dx dy is actually equal to r dr d theta. And during class, I can probably explain to you better on why that is the case. So you're going to wait until then to learn about it. And finally, the last thing that we have to change is the regions of integration. Okay? And so that completes exactly what we need to do, changing three things: the integrand, the differential, and then the regions of integration. So now, how does that actually play out in an example? Unfortunately, my time right now for today is already 32 minutes, so I'm going to stop right here. And we'll talk more about it tomorrow or next video. Okay? All right, talk to you guys later. Bye-bye.